All right, so this is Unit 8, Intermolecular Forces, and 8.1 has the title in Intermolecular Forces Overview. We're just going to kind of highlight the intermolecular forces that we're going to focus on most in Unit 8 as a whole. Now, to initiate the first section here, we're going to talk about the types of attractions that we know thus far, we know up to this point, and what we're going to learn in Unit 8. So the two types of attractions within molecules are intramolecular forces. These occur inside the molecule itself. So if we have a hydrogen chloride molecule floating around, the intramolecular force is the covalent bond that connects the hydrogen and the chlorine atoms. Those two kind of stick together to one another, and they form a more stable molecule in hydrogen chloride. Now, these intramolecular forces can be defined as being either ionic or polar or nonpolar. Polar and nonpolar being the covalent bonds. We also have metallic bonds that we didn't talk about a whole lot in the first semester, but would be hit up more in an AP chemistry class. All of these, though, are known as intramolecular forces because, again, they happen inside the molecule. Unit 8 is going to focus on the things that happen outside the molecule, the intermolecular forces. These are just better known as the attractions between molecules. So if we now have two HCl's, there's one and there's a second one, and they happen to get close enough to each other, they can actually attract each other a little bit. And that attractive force is incredibly important when it comes to the physical properties of the substance. It helps determine whether the substance will be a solid, liquid, or gas at room temperature. It helps determine its viscosity, its surface tension, a whole bunch of other things that we'll talk about throughout this unit. Now, there are multiple different types of intermolecular forces. We're going to focus on four of them. The four forces that we focus on are going to be ion-dipole, hydrogen bonding, dipole-dipole, and London dispersion. So we're going to highlight those in this video. Let's focus on the dipole interactions first, the ion-dipole and the dipole-dipole. Let's try to remember what a dipole is. So recall that a dipole is formed when there is a difference in charge inside of a molecule. So let's just go ahead and draw our simple basic water molecule again. And try to remember that we drew a dipole, partial positive and a partial negative. And what that meant is, let's put up a sodium chloride. And we know in sodium chloride that the sodium gives its electrons to chlorine. So chlorine is totally negative and chlorine is totally positive because there's a complete transfer of electrons from sodium to chlorine. Now, in the case of water, there's not a transfer of electrons. There's a sharing of electrons, hence the covalent compound. And in this case, we don't just give a negative sign or a plus sign. We add this goofy little delta symbol, which means partial negative charge. Okay. So if we look at this molecule, if you kind of cut it in half, you'll notice again the top half of the molecule is negative, and the bottom half of the molecule itself is positive. So when we assign a dipole to this molecule, we put the tail end of the arrow by the hydrogens, the arrowhead by the oxygen. And we say that there's a dipole with the negative side being up towards the oxygen and the positive side being down towards the hydrogens. Again, more of the electrons are gathering towards the oxygen, making it more negative. All right, so that's a dipole. Dipoles of different molecules will actually attract one another. So again, I've got a picture of hydrogen chloride on the right side of this slide. And that's just one hydrogen chloride. But let's say I went ahead and I drew a second HCl. So HCl. And that HCl had, again, a negative side and a positive side. Well, just like magnets, when you get two opposites next to each other, they tend to attract each other. So we're going to have this attractive force between these two molecules. Now, since both of these molecules are covalent compounds, and they both have a dipole, we're going to call this a dipole interaction. Okay. Again, that's to be specific, that's between two, let's say, covalent compounds. Okay, two covalent. Now, the other side of the dipole interactions would be something called like an ion-dipole interaction. So let me write that over here. This is an ion-dipole interaction. Now, that would be the case if I had, well, let's say, HCl, and let's just say I put some table salt in the HCl. So now sodium chloride is an ionic compound. Sodium's got a positive charge, chlorine a negative charge. So since the sodium and the chlorine themselves are actually, when put together, an ionic compound, this type of attraction is called the ion-dipole attraction. So the difference between the two dipole interactions is just whether or not you're working with two covalent compounds, like we did in the previous example, or are you working with an ionic and a covalent compound like we are here. Okay, ionic and covalent. All right. So if we take a look at a whole bunch of HCl's that are kind of floating around in solution, what you'll notice if you put a bunch of arrows in there is that the negatives are all going to attract with the positives, and the positives will attract with the negatives. And this will allow this particular molecule to kind of clump up and stay together. Again, the more interactions there are between the molecules and the stronger those interactions are, the more likely that substance might be a liquid or even a solid at room temperature. All right, let's go to the second one then, hydrogen bonding. So the H obviously stands for hydrogen. Hydrogen bonding. We say hydrogen bonding is fun, and we spell it F-O-N, and there's a reason for that, so just hang on with me. Hydrogen bonding is a very strong version of dipole-dipole interaction, an incredibly strong version. It's so strong that it gets its own name, and it's probably the most widely used, widely researched type of dipole intermolecular force because it's so rampant in biological molecules. It's found all over the place. So hydrogen bonding occurs when fluorine, oxygen, or nitrogen are bonded to hydrogen. So that's where the F-O-N, the fun, comes from. The reason this is such an incredibly strong, these lead to incredibly strong intermolecular forces is because of the electronegativity difference between these elements. For instance, if you look at the electronegativity of fluorine, fluorine has an electronegativity of 4. And hydrogen has an electronegativity of 2.1. The difference between those two, if you do the subtraction there, is 1.9. It's a large difference. That's an enormous difference. Okay? So what that means is if we were to draw a molecule where fluorine was bonded to hydrogen, the majority of the electrons would be right where my red dot is going to be. I'm going to put it right there. All those electrons are getting really close to fluorine because fluorine is just such a strong atom when it comes to pulling electrons. So if we have let's say a water molecule right next to this hydrogen fluoride, let's go with an O and an H and an H. Okay. We think about where the electrons will be. Well, oxygen, if you look at an electronegativity table in the back of your chem manual, oxygen is going to have a higher electronegativity than hydrogen, so the electrons will be pulled closer to oxygen. And if we look at it, what's going to happen in this case is that the fluorine, since it's got more of the electrons, is going to be partially negative, hydrogen partially positive, oxygen partially negative, and the hydrogen partially positive. Now the way I've got these aligned is kind of poor. I'm going to go ahead and flip the water around here. So you can see the attraction. Alignment is actually really important when it comes to intermolecular bonding. And so we get a nice attraction that happens between those two molecules. And again, it's due to the fact that the difference in electronegativities between hydrogen and the fun atoms is so strong that we get this incredibly strong hookup. We get this incredibly strong attraction between the molecules. We see this in everyday life when we take a look at the DNA molecule. So deoxyribonucleic acid. I'm sure in a biology class you've talked about the base pairs, adenine, thymine, guanine, and cytosine. And they're made up of oxygen, nitrogen, carbon, and hydrogen atoms. And they are the things, those base pairs help form that double helical structure of the DNA. And the only reason that the DNA sticks together, that two strands can come together and stick together, is due to hydrogen bonding. So if you look at the picture in the lower right-hand corner there, you see I'm highlighting these 3 dots. Those 3 dots are representing the hydrogen bonds that allow both strands of the double helical structure to stick together. So if it wasn't for hydrogen bonding, you and I wouldn't be here. I wouldn't be broadcasting this video or holding an iPad right now because there'd have been, well, no humans to build it. So it's a good thing we've got hydrogen bonding. Let's go to the final type then. London dispersion forces. The gentleman's last name that found these types of forces or discovered them was London. I don't think it's got anything to do with the actual city itself. London dispersion forces occur when nonpolar molecules, so usually symmetrical molecules, nonpolar molecules, they don't have dipoles. And yet we still see them experiencing intermolecular forces. So this is kind of strange. We should understand why two polar molecules attract each other. To draw that again, if you've got a water molecule and a second water molecule behind it, the oxygens are negative, partially negative. The hydrogens are partially positive. Opposites attract. So we see a nice attraction between those. On the other hand, if we've got something like, let's say methane, carbon, and 4 hydrogens around it, and another carbon and 4 hydrogens around it, the electronegativity difference between carbon and hydrogen is incredibly small. So hydrogen and carbon have almost the same electronegativity difference, so there's really no dipole in these molecules. They're symmetrical molecules. And yet we still see intermolecular forces. So once in a while, these two molecules will actually interact, and they'll attract each other. In fact, if you get methane cold enough, it'll turn into a liquid. In some of the seas, some of the oceans or lakes in distant planets are actually methane lakes. These forces are going to exist due to small dipoles that are formed on these nonpolar molecules. And these small dipoles are formed because moving electrons that spin around an atom can cause an uneven charge. So if you look at two helium atoms, which are very neutral, once in a while electrons will become unevenly distributed. So you'll have a lot of electrons over here, making more of a negative side to that atom. And you'll have the electrons be pushed away, making a positive side to this atom. And so because of that, you'll get the attraction between those two atoms. They'll actually attract one another just a little bit. Now, it's a very weak attraction, and it's very brief, but it is an attraction nonetheless. Larger molecules, really big molecules, have more places where this type of attraction can occur. There are more chances for London dispersion forces to do their thing. And so these larger molecules are usually harder to break up. So if I take a look at, these are two hexane molecules. They're pretty big molecules, but they're very symmetrical. They're both nonpolar. But because they're big, there's a lot of London dispersion forces. So the attraction between the molecules is pretty heavy. And to really lead you to why that's important, well, the more attractions there are, again, the more likely that this particular molecule will be a liquid at room temperature. And hexane, in fact, is a liquid at room temperature. In fact, the larger the molecule gets, the more energy you actually have to give to it, the more you have to heat it up in order to vaporize it. So if you think about methane, that's the stuff that comes out of our gas spigots for our Bunsen burners. It's a gas at room temperature. It's a very small molecule, 1 carbon. But if you look at hexane, in the image that you see here, it's got 6 carbons. It's got 14 hydrogens. So it's a much bigger molecule. So there's more London dispersion forces, more attractions, and it's harder to break apart this molecule in order to turn it into a gas. All right, that's 8.1.